Hello everyone, welcome back to the video. So today we are going to be going over how to solve half-life problems. This is day 2 of half-lives. The do now is to define a half-life. Remember, a half-life is the amount of time it takes for a half of a radioactive isotope or radioisotope to decay. And when solving half-life problems, what should we be searching for first? The answer is the cycles, or the letter C in that formula. Your homework: if you're in periods 1 and 8, you do not have homework. If you're in periods 3 and 7, you are finishing Lab 7's graph for homework. Just a heads up, your nuclear chemistry test is going to be given on Thursday, October 22nd, which means that anyone who took the exam in person last time will be taking it at home. And any person who took the exam at home last time will be taking it in class. I'm flip-flopping it just to make it fair. All right, so today the plan is we are going to be going through all 5 types of half-life problems, and then that's really going to be it. So the half-life of iodine-123 is 13 hours. How much of a 64 milligram sample of iodine-123 is left after 39 hours? So the first thing I like to do is just write down what I'm given. So according to the problem, it says the half-life is 13 hours. So I'm just given the half-life straight away, which is H. So that will be 13 hours. It also tells me how much of a 64 milligram sample is left. So based on the English in that question, it's just saying how much of that original mass is left. So this 64 is the original mass. So MO 64 milligrams. And finally, it says after 39 hours. Whenever you see the word after and then a time period, that means that is the time passed, or the lowercase t. And that's, again, 39 hours. Couple little disclaimers in this problem. First, you'll know the difference between the time passed and the half-life, because the time passed is always going to be a larger number than the half-life. And you're going to know the difference between your original and final mass, because your original mass will always be a higher number than your final mass. So what are you looking for here? You're looking for the last letter, which is not given, your final mass, which I'm going to label for now as X. So this is a final mass problem. All right, so let's get started. So the first step is to write out our formula, which, remember, this formula is not given on the periodic table. So you do need to know it. The formula is T over H is equal to C. Your T is 39 hours. Your H is 13 hours. And I'm just going to pull up a calculator real quick on the screen so you guys can see what I am doing. So again, that is 39 divided by 13, and that comes out to be 3. So you have 3 cycles here. And so what do we do for our cycles? We are going to write out our original mass, and we're going to keep dividing it by 2 until we get 3 half-life cycles done. So let's get that started. So first we have 64 milligrams. And let's get into 1 cycle. So 64 divided by 2 comes out to be 32. So our first value is 32. Our second cycle, that would be 32 divided by 2, comes out to be 16. And our third cycle is just 16 divided by 2, which comes out to be 8. And so your answer is 8. What units, though? The easy part with this topic is that your units stay the same for your topic. So your time is going to stay the same, so hour. Your mass is also going to stay the same, milligram. So this would be 8 milligrams, and that is your answer. Right, let's go on to example number 2. Example number 2 says, if 13.125 grams of K42 remains undecayed after 62 hours, what is the original sample size? All right, so again, first step, we're going to write down what we have. So what do we have? We are told that 13.125 grams remains undecayed. So that language saying that remains undecayed means that this is our final mass. So this is 13.125 grams. Next, we see that it's saying this after 62 hours. So that means that that is our time passed. Now remember, in the guide where I was going over what happens if you have one mass one time, where do you go? You go to table N of the reference table. So if I open up table N of the reference table, and I look for potassium 42, that comes out to be 12.36 hours. Again, potassium 42, 12.36 hours. So again, 12.36 hours. And that is our half-life. So what's left? It's asking for the original sample size, and that's just our original mass. So the original mass is our X. All right, so now what's the first step of doing this? We are going to try to find our number of cycles. So to do that, we just put in our formula. T over H is equal to C. We have our T as 62. We have our H as 12.36. So we just put that in the calculator. 62 divided by 12.36. But oh no, this is a decimal. It's not a whole number like we've had before. So what do? If this ever happens to you, you're going to round to the nearest whole number. So this would round to be 5. And now what we're going to do, since we have our final mass but not our original mass, we're going to do the same line as we did before, except we're starting with our final mass. So we're going to start with the 13.125 grams. And this time we're going to go backwards. The plan is we're going to, instead of divide the 13.125 by 2, we're going to multiply it by 2. Because remember, the original mass is always bigger than the final mass, so it would only make sense. 5. So 13.125 times 2 is 26.25. 4. So 26.25 times 2 is equal to 52.5. 3. So 52.5 times 2 is equal to 105. 2. 105 times 2 is 210. And finally, 1. 210 times 2 is equal to 420. So that means your X is equal to 420 as well. But what are the units? Remember, the units for the masses are the same. So if this mass is in grams, that means this mass will also be in grams. And that's our answer. Anyway, so on to the next problem. Chromium-48 has a short half-life of 21.6 hours. How long will it take 360 grams of chromium-48, to decay to 11.25 grams? Just to clarify, by the way, that previous problem that we worked on, this is a original mass problem. So let's see what we have. So it straight up gives us the half-life. It tells us the half-life is 21.6 hours. So our H is equal to 21.6. It tells us, it gives us 360 grams of chromium to decay to 11.25. We know the bigger number is our original mass, so our original mass is equal to 360. Wow, that does not look like a 3. Let's fix that real quick. Perfect. And we see our final mass again, which is smaller than our original, to be 11.25 grams. Okay, so what are we looking for? We're looking for our last value, time passed. So now, this is a time passed problem. So the first thing that we do is we are going to write down our formula, which is T over H is equal to C. Our T is going to be X, because that's what we're looking for. Our H is 21.6 hours, but oh no, we don't have a C. We need to have at least 2 things for this formula to work. So what do? We have to look for the cycles. So to look for the cycles, we are going to have to keep cutting our original mass in half until we get to our final mass. So we start off with 360. Oh, let me do that in a different color. 1. So 360 divided by 2 is 180. Two. 180 divided by 2 is 90. 3. 90 divided by 2 is 45. 4. 45 divided by 2 is 22.5. And 5. 22.5 divided by 2 comes out to be 11.25. We do not keep going because we've reached our final mass. So we have 5 cycles. So we're going to set this whole equation equal to the number 5. Now, if you're someone who struggles with math, here's what you do next. You will put a 1 under the 5, and you're going to cross multiply to try to find what that x value is. So it comes out that x is equal to 5 times, which let me make that into a dot instead. Hold on. 5 times 21.6. And when you multiply those values, that's 5 times 21.6, comes out to be 108. So your x comes out to be 108. What is the time? What is the units? We see our masses are both in grams. So that means that this is going to follow the time, which is in hours. And that is your answer. Okay, next one. Problem number 4. What is the half-life of an unknown radioactive isotope or radioisotope if a 66 gram sample decreases to 8.25 grams in 48 minutes? Okay, so what we're going to do for this problem is first we are going to write down what we have. So tells us that it's straight up asking for the half-life. So we know that the half-life is our x. It says a 66 gram sample decreases to 8.25. Remember, the bigger mass is our original mass. So our original mass in this case is 66 grams. And our final mass comes out to be 8.25 grams. Our time passed comes out to be 48 minutes. Let me fix that 4 real quick. Okay. So, let's get into this problem. So the first thing we have to do is look for our number of half-lives or our cycles. So, that is again T over H is equal to C. We don't have our H, that's our X, but we do have our T as 48 over X is equal to, but we don't have our cycles. What do? We are going to take our original mass and keep dividing it by 2 until we get to our final mass. So we start off with 66. Okay. 1. So 66 divided by 2 is 33. 2. 33 divided by 2 is 16.5. And 3. 16.5 divided by 2. That is not what I want. 16.5 divided by 2 comes out to be 8.25. Now the reason we don't keep going is because we've reached our final mass. So how many cycles do we have? 3. So again, for my students who struggle in math, let me walk through how to do this. First, you put a 1 underneath the 3. Then we're going to cross multiply. So this problem comes out to be 48 is equal to 3x. We want to get the x by itself, so we divide both sides by 3. That gets rid of that. And your x comes out to be 48 divided by 3, which is 16. What units is that? We try to look at the same units. We got same unit for mass as grams, and we'd have the same unit for time, which would be minutes in this case. So this would be 16 minutes, and that is your answer. All right, last problem. And by the way, this problem was a half-life problem. It was searching for the half-life. Last problem. As the song goes, one of these things is not like the other. This is a little bit strange. It's a little bit different. So, cobalt-60 is used in some cancer radiation therapies. What fraction of a sample of cobalt-60 will remain undecayed after 10.52 years? Okay, so the reason why this is strange is because it's asking you for a fraction. It's not asking you for a mass or for a time. So, anyway, let's get into this. So first, we're going to write what it has. So we see the word after and a time period. So that means this gives us the time passed as 10.52 years. But oh no, where do I find the half-life? We find the half-life on table N of the reference table. So on table N, we see cobalt-60 has a half-life of 5.271 years. So again, our half-life is 5.271 years. Okay, now if you look at this and you get confused, do not, because the first step's still the same. We have to find our number of cycles. So again, that is T over H is equal to C. So our T is our 10.52. And our H is our 5.271. So again, we take our 10.52, divide it by our 5.271, and that comes out to be 1.999. Again, big number. Oh no, what do? We round to the nearest whole number, and the nearest whole number would round this to be 2. So now that we got 2 cycles, what do we do from here? What I'd recommend is, just so it has some familiarity, if they don't give you a mass at all and they're asking for a fraction, you can pretend that your original mass is just 1. And you're trying to find the final mass. Or final fraction in this case. So you can think of it kind of like following the same procedure as your final mass type of problem. So again, if we start with 1, 1 cycle would make that into a half. Because remember, we want fractions, not decimals. And 2 cycles would turn this half into a quarter. So your answer is a quarter. No units needed for fractions. Anyway, if you have any questions, please feel free to message me at any time. I am available through Remind at any point, so just please feel free to ask me a question, or you can send me an email. As always, thank you for listening, and I hope you all have a wonderful, wonderful day.